He has received fellowships for his work from the Pew Foundation, the University of Notre Dame, and the Templeton Foundation. He has written many articles and book chapters on such topics as the fine-tuning of the cosmos as evidence for design, quantum mechanics, Asian philosophies and religions, the doctrine of Christian atonement, evolution and original sin, petitionary prayer, the relation of the mind to the body, and the metaphysics of the natural world. Welcome him as he comes to speak.
I'd like to thank the Greer Herd Forum for inviting me today, and everybody here for being here. One of the most persuasive evidences for the existence of God from the cosmos is the argument from the fine-tuning of the cosmos for the existence of God, the so-called anthropic fine-tuning. This refers to the fact that the laws, initial conditions, and fundamental parameters of physics must be precisely set for life to exist. The relevant kind of life depends on the hypothesis that the evidence is supposed to support, which in the case of theism is embodied conscious agents who can interact with each other based on what they perceive as moral criteria. And we'll see why later. For convenience, I will simply use the abbreviation ECAs for such agents. The most commonly cited case of anthropic fine-tuning is that of the cosmological constant. If it were not within 1 part of 10 to the 120th power, that's 1 followed by 120 zeros, of its theoretically possible range of values, either the universe would expand or collapse too quickly for galaxies and stars to form, and hence ECAs to exist. There have been a variety of challenges to the fine-tuning evidence itself, and whether it supports the existence of God or a multiverse. I have developed a detailed argument elsewhere that the fine-tuning evidence does provide strong confirmatory evidence for theism over naturalism. Further, I have argued that the underlying mathematical structure of the universe is much more elegant than would be expected under naturalism, something often noted by scientists. Here, I primarily want to explore another kind of fine-tuning and its implications for this debate. The fine-tuning of the universe for developing scientific technology and being scientifically highly discoverable, which I will call the fine-tuning for discovery. By this fine-tuning, I mean that the laws, fundamental parameters, and initial conditions of the universe must be just right for the universe to be as discoverable as ours. After presenting examples to illustrate this kind of fine-tuning, I will argue that if this kind of fine-tuning exists, in general, it cannot be explained by a multiverse hypothesis, by far the leading non-theistic explanation for anthropic fine-tuning. Further, I will show how the idea that the universe is fine-tuned for discovery answers some other commonly raised objections against the fine-tuning argument. And finally, I will look at its potential predictive and explanatory power. Finally, to be absolutely clear, my project in this paper is not so much to argue for the existence of God, as I've done elsewhere in the debate on fine-tuning, as it is to explicate a place where there's potentially new evidence one way or another. This is in keeping with the spirit of scientific inquiry. Background. Many scientists and others have commented on the seemingly miraculous intelligibility and discoverability of physical reality. Most famously, Albert Einstein and Eugene Wigner. Recently, the idea has been developed more carefully by Mark Steiner in his 1998 book, Mathematics as a Philosophical Problem, Harvard University Press. Steiner presents an array of examples where, in their attempts to discover the underlying laws of nature, physicists successfully use lines of reasoning that only make sense if they were implicitly assuming that the world was structured for discoverability. He concludes that the world, quote, looks user-friendly. This is a challenge to naturalism, end of quote. In a project I am near completing, I have attempted to quantitatively test this idea that the universe is in some sense fine-tuned for discoverability by calculating the effects on our ability to discover the major and/or important domains of reality, such as cosmology, microbiology, and the past history of the Earth, by varying some of the fundamental parameters of physics. The cases I will cite involve original calculations. They have been verified by at least 2 physicists. The calculations referred to in this paper have been sent to Sean Carroll, and along with the draft of this paper can be found on my website. Just Google my name, Robin Collins. Nonetheless, because they are not part of the peer-reviewed literature, I do not expect everyone to accept their legitimacy. For those who do not, they should take this paper conditionally, as spelling out the implications that this sort of fine-tuning would have if it all works out. I have found about a dozen cases of this kind of fine-tuning. Below are 3 illustrative examples involving the fine structure constant. Further elaboration of these examples can be found on my website. Later, with all the calculations, later in the course of articulating the significance of predictive and explanatory power of this sort of fine-tuning, I will look at 2 other examples in the cosmological context. The fine structure constant, commonly designated by the Greek letter alpha, is a physical constant that governs the strength of the electromagnetic force. A small increase in alpha would have resulted in all wood fires going out. Yet harnessing fire was essential to the development of civilization, technology, and science. For example, the forging of metals. Why would an increase in alpha, fine structure constant, have this effect? The reason is that in atomic units, the non-relativistic Schrodinger equation is not dependent on alpha. And hence, everyday chemistry and the sizes of everyday atoms are not affected by up to a 9-fold increase or any decrease in alpha. In most regards, the world around us would look the same with such a change in alpha. The combustion rate of wood, for example, would remain the same with such a change. In these units, however, the rate of radiant output of a fire is proportional to alpha squared. For example, a 2-fold increase in alpha would cause the radiant output of an open fire to be 4 times as great, the kind of fire shown up there. A small increase in alpha, around 10 to 40%, causes the radiant energy loss of an open fire to become so great that the energy released by combustion cannot keep up, and hence the temperature of the fire would decrease to below the combustion point. The above argument applies to all forms of biomass, not just wood, because they're based on chemistry. Since in atomic units, everyday chemistry does not change with the change in alpha considered above, the combustion rate would remain the same for these. Although some biomass is much more combustible than wood, such as oil, these types of biomass either are not readily available to would not be readily available to primitive carbon-based ECAs, or they would be less suitable for the size of fires needed for smelting metals. Hence, it would be far less likely that primitive carbon-based ECAs would have regularly used them and thus discovered the smelting of metals. Going in the other direction, if alpha were decreased, light microscopes would have proportionally less resolving power without the size of living cells or other microscopic objects changing when measured in atomic units. As is, the maximum resolving power of light microscopes is about 0.2 microns, millionths of a meter, which happens to be the size of the smallest living cell. The only alternative light microscopes for seeing the microscopic world is electron microscopes. Besides being very expensive and requiring careful preparation of the specimen, electron microscopes cannot be used to see living things. Thus, it is quite amazing that the resolving power of light microscopes goes down to that of the smallest cell, but no further. If it had less resolving power, some cells could not be observed alive. The fine structure constant, therefore, is just small enough to allow for open wood fires and just large enough for the light microscope to be useful so it can see all living cells. Another major effect of decreasing alpha would be on electric transformers, motors, and paleomagnetic dating. The reason that is in atomic units, the strength of magnetic fields produced by an electric current, along with that of permanent magnets, is proportional to the square of the fine structure constant. Yet, excluding elements with atomic numbers around the value of gold or higher, electrical resistance, chemistry, the size of objects, etc., remain the same with a decrease in alpha. Thus, for instance, a 5-fold increase in alpha would result in a 25-fold decrease in these magnetic fields, requiring far more windings and transformers and motors, which would greatly increase power losses. If you ever looked into a motor or transformer, you see lots and lots of windings. Just open one up, and power loss of resistance is a major source of power loss. It's still not critical, obviously, because we have these motors and transformers all over the place, but it would be critical with this decrease in alpha. Since transformers and motors are the basis of our technological ladder, this would have a major negative effect. Thus, the technology slash discoverability optimality range for alpha is squeezed into a fairly small range around its current values. I showed there with the star and up and below, and it's over a huge range of values. It's got to be right there to maximize, to have the kind of technology we have. Thesis of discoverability. If the cases of discoverability are indeed coincidental under naturalism, the thesis that they directly support is what I will call the discoverability thesis. This is the thesis that the universe is non-accidentally structured in such a way as to be highly discoverable. If we define naturalism to include the thesis that any apparent teleology in the universe is accidental, then the discoverability thesis is in conflict with naturalism. In arguing for the discoverability thesis, I ultimately argue that the level of discoverability in our universe is much more coincidental than one would expect under naturalism. Specifically, I argue that among the alternative universes generated by varying the parameters of physics, such as moving the fine structure constant around, a very small proportion are as discoverable as ours when the parameter itself is used as a natural measure of proportion. I call this the discoverability coincidence thesis. Finally, the data suggest, it's the data that's suggesting, I want to emphasize that, it's not a priori commitment to this, suggests a particularly strong version of the discoverability thesis, what I call the discoverability slash livability optimality thesis. Within the range of values of a given parameter, P, that yield near optimal livability, you can see it up there, P will fall into that sub-range of values. So you look at the optimal livability value, then P falls into the sub-range of values that maximize discoverability and given constraints of elegance, etc., are not violated. Although my argument does not require this thesis, in every case I was able to make calculations regarding whether the fundamental parameters of physics are optimized in this way, they appear to pass the test. This alone is significant since this hypothesis is falsifiable in the sense that one could find data that potentially disconfirms it. In particular, cases in which, as best we can determine, changing a particular fundamental parameter, such as the fine structure constant, increases discoverability while not negatively affecting livability or elegance. This is just the sort of criteria that Professor Carroll said last night was so important in the scientific enterprise and for good theory. Below, I will look at a case from cosmology where this thesis could have been disconfirmed but was not. New ideas are very subject to misinterpretation. So before moving on, it is important to clear up a misunderstanding of what I am claiming. Namely, that I am arguing that this is the most discoverable possible universe. We can certainly imagine what initially might seem to be more discoverable universes and much less discoverable universes. We cannot draw any conclusions from this, however, unless we know the underlying laws of those universes. For example, an imagined more discoverable universe might require laws that are far more complex or inelegant, thereby taking away from their seeming discoverability. Further, theists should not expect God to create a maximally discoverable universe because there are other trade-offs, elegance, livability, and so forth, that God must consider. My main thesis, therefore, is that the level of discoverability of the universe is highly coincidental. If we are going to test this hypothesis, we must restrict ourselves to alternative universes chosen by a method that, one, is not a priori biased for or against discoverability coincidence thesis, and two, such that we can make reasonable determinations of the level of discoverability of each alternative universe. That is why the possible universes being considered are those with different values of the fundamental parameters, and why I restricted the DLO, the discoverability, livability, optimality thesis, to those universes with different values for a given parameter but the same underlying laws. So far, I've talked about the discoverability thesis. What is theism's relation to it? God and discoverability. God is often defined as an omnipotent, omniscient, perfectly good being that created all contingent reality. Because God's goodness is the only attribute that tells us anything about what God would do, theism leads us to expect that God would create a reality structured to realize positive and, if possible, an optimal balance of value over disvalue. Thus, theism renders unsurprising any feature of the world for which we could glimpse how it could be a moral or aesthetic value, such as the existence of embodied conscious agents, as in the case of the anthropic fine-tuning argument, or the elegance and harmony of the underlying laws of nature. A generic design hypothesis doesn't tell you anything, so it doesn't gain confirmation. This is a real important point to stress. Yes, you actually can confirm certain attributes of God's goodness, for instance, because if you don't have that, you have no expectation about whether it's going to be embodied conscious agents, so those hypotheses, alternative intelligent design hypotheses, are not confirmed. If we can glimpse how discoverability might be of value, then theism would also render it unsurprising that the universe is highly discoverable. Why might discoverability be of value? First, it allows us to develop technology, which in turn allows us to greatly expand our ability to improve our conditions. Second, it seems valuable in and of itself. The fact that governments spend billions of dollars on research into the fundamental structure of the cosmos, and that the public generally supports this, shows that collectively we find such knowledge of value. So although theism does not require that the universe is highly discoverable, it renders it unsurprising and hence fits much better than naturalism. Significance. Now we are ready to see the significance of the above discoverability thesis for the debate over God and cosmology. I begin with the multiverse hypothesis. A significant number of philosophers and scientists respond to the anthropic fine-tuning evidence by claiming that it is a brute fact that does not need explanation. I find such a response incredible when one looks at the degree of fine-tuning. 1 part in 10 to the 120th power in the case of the cosmological constant, and a ridiculous 1 part in 10 to the 123rd power for the volume of phase space, that is the space of possibilities used by physicists of a universe having an entropy as low as ours. Speaking for myself, almost anything is more believable than that occurred just on its own by chance. Thus, in order to believe that, I would have to be given an exceedingly strong argument that there was no other alternative, not the kind of arguments typically offered against the theistic alternative. At the very least, such evidence puts a burden on naturalists to provide powerful reasons for rejecting the theistic explanation or coming up with an alternative. A more common response among cosmologists is to invoke a multiverse to explain the fine-tuning. According to this hypothesis, there is a very large, if not infinite, number of regions of space-time with different values of the fundamental parameters of physics, different initial conditions, and perhaps even different laws of nature. It then claims that in a sufficiently varied multiverse, it is no surprise that some universe is structured so that observers will arise in it. Finally, it invokes the so-called observer selection principle, which is the tautological claim that embodied observers can only exist in a region of space-time that allows them to exist. This renders it unsurprising that as observers we find ourselves in an observed structured region of space-time, since it is impossible for us to exist in any other type of region. The observer selection principle is essential to the multiverse explanation because it prevents it from undercutting the need to explain other seemingly surprising events and features of the universe. For example, normally one would think that it's too coincidental for a six-sided die to land, flip it, roll it 50 times in a row on 4 just by chance. Yet in a large enough multiverse, someone will observe this to happen. Nonetheless, it is still improbable that a generic observer in a generic multiverse will see such an occurrence. Hence, purportedly, the multiverse hypothesis combined with the observer selection principle can render it unsurprising both that the observers exist and that we, considered as generic observers, find ourselves in an observer-structured universe, while at the same time not undercutting normal claims of improbability. Because of its reliance on the observer selection principle, the multiverse can only directly render unsurprising that we find ourselves in an observer-structured universe. Because of this limitation, it cannot, without additional hypotheses, explain the fine-tuning of the constants or the fine-tuning for discoverability. As I've argued elsewhere, with regard to the former, the problem is that those universes that do not have life-permitting values for the fundamental parameters of physics, such as the cosmological constant, and are sufficiently large, for example, infinite, which is typical of modern cosmology, will be dominated by isolated observers arising from thermal fluctuations, which you've heard a lot about, Boltzmann brains. In fact, given the extreme fine-tuning of the constants, there will be vastly more of these universes than ones dominated by ECAs like us. So even for non-fine-tuned values of the parameters, there will be thermal fluctuations that give rise to those observers. Thus, the parameters of physics are not fine-tuned for observers, because they exist in all of those values. Rather, they are fine-tuned so that ECAs can arise that can significantly interact with one another. But because of its reliance on the observer selection principle effect, without further postulates, the multiverse only implies that we'll find ourselves in an observer-structured universe. Thus, it cannot of itself directly explain the actual anthropic fine-tuning. That is why, as generic observers, we find ourselves in a universe whose fundamental parameters allow for embodied conscious agents. The existence of these fluctuations universes therefore poses a problem not just for a multiverse explanation of the low entropy of the universe, but more generally for explaining the fine-tuning of the constants. Now, of course, you could develop a measure to get around this, but I think this points out another weakness. It's not in my paper here, of the multiverse explanation. You have to have a very special multiverse in many ways to even get one ECA, body conscious agents permitting universe. So there's already a kind of fine-tuning of the laws up another level, that you haven't completely eliminated the fine-tuning. So that's another problem, I think, with the multiverse. According to the thesis I am proposing, the universe is not just fine-tuned so that ECAs can exist, but that they can develop technology and discover its nature. If this is indeed the case, the multiverse hypothesis would also run into a major problem explaining this fine-tuning. The reason is that there seems to be no necessary connection between a universe being ECA permitting and its being discoverable beyond that required for getting around in the everyday world. Thus, if, because of the fine-tuning for discoverability, the proportion of observer-permitting universes that are as discoverable as ours is really small, it would be very improbable under a generic multiverse hypothesis that as generic observers we would find ourselves in such a universe. So the fine-tuning for discoverability, if legitimate, presents a further problem for the multiverse as a complete explanation of the fine-tuning. Since this discoverability is not surprising under theism, if it is truly highly coincidental, it provides, under naturalism, it provides further data in support of theism and thus moves the debate forward. Irrelevant to life objection. I will now consider how the discoverability theses help to answer a common objection usually raised by physicists against anthropic fine-tuning. Namely, many features of the universe seem irrelevant for the existence of life. This objection is nicely stated by Sean Carroll. After listing some reasons to be skeptical of fine-tuning claims, Carroll states that, but in fact there is a better reason to be skeptical of the fine-tuning claim. The indisputable fact that there are many features of the laws of nature which don't seem delicately adjusted at all, but seem completely irrelevant to the existence of life, end of quote. One commonly used example, by Carroll, Stephen Weinberg, and Mario Livio, is that the existence of extra generations of particles, such as the muon, a particle that is in all ways like the electron, except being much more massive. Such particles do not seem in any way needed for life. Along similar lines, Carroll takes issue with the theistic explanation of the low entropy of the universe, correctly noting that only a universe with a local region of low entropy is needed for life. Carroll then claims that in creating a universe with low entropy throughout, God would have had to fine-tune the universe far more than would be necessary for life. Thus, he states, quote, poses a bigger problem for the God hypothesis than for the multiverse, end of quote, though Carroll does not really explain why in the article in question that appears in the Blackboard Reader in Science and Christianity. Contrary to what Carroll assumes, it is not clear why under theism every feature of the universe would have to serve a purpose. Clearly not everything, such as the number of moons of Jupiter, will have a purpose. But even if theism does not entail that every ingredient in the fundamental structure has a purpose, or even if it does entail this, at least for the fundamental structure, discoverability along with considerations of elegance could offer a way of explaining them. To elaborate, the extra generations of particles that Carroll refers to could very well help with humans discovering the fundamental structure of matter. For instance, these extra generations fall into a highly symmetric pattern, as can be seen up on the slide. 3 for each of the 2 types of quarks, top left, and 3 for 2 types of leptons. This symmetry suggests they are clues to an even deeper, more elegant theory. Further, they could help in discoverability in other ways. For example, according to the June 2012 issue of Symmetry magazine, a publication of Fermilab and Stanford Linear Accelerator Center, the muon, the particle perhaps most commonly cited as an added extra whose existence seems purposeless, is playing an increasingly important role in particle physics. According to Chris Pauly, one of the Fermilab physicists involved in muon research, one reason the muons are special is that, quote, they are light enough to be produced copiously, yet heavy enough that we can use them experimentally to uniquely probe the accuracy of the standard model, end of quote. Further, the article notes, quote, today scientists can manipulate the muon and use it as a tool not only for particle physics research, but also for cosmology, archaeology, and public safety. With regard to the low entropy of the universe, having a low entropy throughout the entire universe makes it much more discoverable for at least 2 reasons, one of which I'll only mention here. A universe that has a low entropy over a vast region is necessary for us to observe other stars and galaxies, and thus to understand the Big Bang origin of our universe. We can measure the Hubble constant, see it expanding. We couldn't see it expanding in our own galaxy. The existence of stars and galaxies requires low entropy. As Carroll notes, if the region of low entropy were not large enough, the universe would be devoid of other galaxies. Of course, one could respond that God could have created a universe that did not originate in a Big Bang and, for instance, only contained one galaxy. This, however, is irrelevant, since the question is why a universe such as ours that originated in a Big Bang and has the same underlying laws of physics has a low entropy throughout. Discoverability has an answer to this. It does not purport to answer why God did not create another kind of universe with radically different laws or origin, such as a Star Trek universe in which we could warp drive to discover other stars. In light of the possibilities that discoverability and also elegance offer for understanding the universe is this way, let me suggest that objections like the above run the risk of being an ungodly appeal to gaps. Just because we do not understand the reason God would have created the world with a particular fundamental feature does not mean there is not one. Besides this ability to make sense of the items mentioned above, below I consider an example of the discoverability, livability, optimality thesis, potential predictive power, cosmic microwave background radiation. The most dramatic confirmation of the DLO, that thesis, is the dependence of the cosmic microwave background radiation, CMB, on the photon to baryon ratio. The CMB is leftover radiation that permeates space from the Big Bang that has been redshifted into the microwave region of the electromagnetic spectrum. Because its source is in the Big Bang, the CMB tells us critical information about the large-scale structure of the universe. For example, physicists John Barrow and Frank Tipler point out, quote, the background radiation has turned out to be a Rosetta Stone on which is inscribed the record of the universe's past history in space and time. Much of the information in the CMB is in very slight variations in its intensities of less than 1 part in 100,000 in different parts of the sky. Since the CMB is already fairly weak, this implies that within limits, the more intense it is, the smaller the fluctuations, the smaller it is, and hence the more intense it is, the smaller the fluctuations one could detect, and hence the better tool it is for discovering the universe. Now, the intensity of the CMB depends on the photon to baryon ratio, which is the ratio of the average number of photons per unit volume space to the average number of baryons, protons plus neutrons per unit volume, and it's fairly constant throughout most of the history of the universe. At present, this ratio is approximately 1 billion to 1, billion photons for every one of these neutrons plus protons, but it could be anywhere from 1 to infinity. It traces back to the degree of asymmetry in matter and antimatter right after the beginning of the universe. For approximately every billion particles of matter, particles of antimatter, there was 1,000,000,001 particles of matter. So far, it is a mystery why this ratio is what it is. Even if physicists can give a further explanation for why it has the value it does, the question would still arise as to why that deeper physics instead of some other. The only livability effect this ratio has is on whether or not galaxies can form that have near optimal livability zones. As long as this condition is met, the value of this ratio has no further effects on livability. Hence, the DLO predicts that within this range, the value of this ratio will be such as to maximize the intensity of the CMB as observed by typical embodied conscious agents. According to my calculations, which have been verified by 3 other physicists, three of them cosmologists, to within the margin of error of the experimentally determined parameters, the value of the photon to baryon ratio is such that it maximizes the intensity of the CMB and falls off rapidly for values of this ratio different from that of our universe. This is shown in the slide right here. And so notice in that slide right there, that's where we are 1. It's the value over the value in our universe. Right there it maximizes. And when I did that calculation, I was actually somewhat shocked because I didn't know how it was going to turn out. In fact, it is easy to see that this prediction could have been disconfirmed. In fact, when I first made the calculations in the fall of 2011, I made a mistake and thought I had refuted the DLO, since those calculations showed the intensity of the CMB maximizes at a different value somewhere else. So I thought it was wrong. I tested a thesis and it turned out I thought it was wrong. But then I recalculated and found my error. So not only does the DLO lead us to expect this ratio, but provides an ultimate explanation for why it has this value. Whatever other explanations we find based on some deeper physics. This is the case of a teleological thesis serving both a predictive and explanatory role. And this, of course, was very inspiring once I found this, to continue pursuing it for other parameters, and it continued to work out. Objections. Discoverability selection objection. One objection to the above argument is that there is a discoverability selection effect. One form of this objection takes as the claim that if a domain were not discoverable, we would not know what we are missing. The simplest answer to this objection is that this is not generally the case. For instance, suppose the fine structure constant were 50 times smaller. In that case, light microscopes would still resolve objects down to 10 microns. Yet if ECAs could exist in such universe, they could observe some cells and thus develop cell theory and gain indirect knowledge that there were cells less than 10 microns in size, and yet wish they had an instrument that could see them. Or as another example, we could have lived in a universe in which the photon to baryon ratio was substantially different, but where a very weak, much weaker CMB was still detectable. Then one could show that the photon to baryon ratio in our universe would maximize the intensity of the CMB and hence make it more useful than the other value ratio of this value, as I thought initially was actually the case. Cherry picking objection. Another possible response to cases of discoverability is that they involve cherry picking. One looks for and finds the information that confirms one's hypothesis, ignoring all the disconfirming evidence. There are several types of cherry picking. First, one might pick features of the world that are helpful for discovery and ignore those features of the world that hurt discovery. Since there are so many domains that could be discovered, it seems likely that one could always find some features of the world that are helpful for discovery with almost any kind of world that could give rise to ECAs. This objection can be avoided by restricting ourselves to only considering widely recognized major domains: cosmology, geology, cell biology, the fundamental microscopic structure of the world, and the like, and the major tools for those domains, such as the light microscope, radioactive dating, and the CMB, and very foundational things to our technology, like, electric motors, all that sort of thing. Further, one might worry that the tools for discovery are often not obvious until they are developed. Hence, if the values of the parameters were different, there might be other possible tools that ECAs could develop that we are not presently aware of. For the major domains of discovery, this is typically not the case. For example, alternative values of the fine structure constant will not give rise to alternative forms of radiation that would be as good as light for observing cells. Hence, for at least a wide range of values of the fine structure constant, there will be no adequate replacement for the light microscope. Or consider the cosmic microwave background radiation. Different values of the photon to baryon ratio will not give rise to an alternative form of radiation that is a substitute for the CMB, because the CMB is something given off by the entire structure of the cosmos at recombination, and there's nothing like that that would come into being. In conclusion, looking for cases of fine-tuning for discoverability has the potential of providing a new set of empirically based evidence with regard to the debate whether the universe is teleologically structured or indifferent to our existence. It thus has the promise of substantially moving the debate forward. And I should say there's a lot of other constants. I've got a little extra time here. There's a lot of other constants or parameters I looked at. Strength of gravity, if you given by the gravitational analog to the fine structure constant. If you decrease that too much, a habitable planet has to get so large that its density of radioactive elements have to go down. Otherwise, there's too many volcanoes, and then it decreases livability. And so then you wouldn't be able to do radioactive dating. Then I looked at the weak force and the carbon-14 dating. Potassium argon depend on that not being too strong, for instance. And quite a few other cases. So it's an ongoing project, but it seems to be working out so far. All right, thank you.
So as a physicist, I have to say that at face value, the idea that the physical world that we are faced with is in some sense maximized for discoverability is, to put it mildly, hard to swallow. I think it is very clear that we could easily invent other laws of physics that would make the world much more easily discoverable. Classical mechanics is much more discoverable than quantum mechanics is. We would have discovered it hundreds of years ago. Even within the framework of quantum field theory, it's very easy to imagine adding extra forces to the standard model, which would make it easier to study the nature of matter without actually studying its structure, without actually changing its structure. Now, Robin knows this perfectly well, therefore he defines his thesis to exclude those possibilities, and he says he's only going to look at the known laws of physics, but with certain values of the parameters, and claim that those values of the parameters are chosen to be discoverable. So let's look at an example. My favorite example is the Higgs boson, which we just discovered in July 2012. And it was a big deal when we discovered the Higgs boson. News worldwide, front page. Physicists breaking down in tears and laughter and joy. Why were they so happy? Well, it's a big part of physics, but also they were happy because we had been looking for the Higgs boson for a long time, and we hadn't found it. We looked for it in the 1980s at the superproton synchrotron, also at CERN outside Geneva. We looked for it at the Tevatron at Fermilab outside Chicago. We did not find it. We also looked for it at the Large Electron Positron Collider, also at CERN. We looked for it at the Stanford Linear Accelerator and did not find it before we finally found it. It took thousands of physicists, decades of effort, and billions of dollars to find the Higgs boson. And if you went and visited those physicists and said, you know what, I think it's pretty clear that the mass of the Higgs boson is maximized to be discoverable, they would probably slap you. They would certainly be a little bit upset. Now you might say, well, but maybe if the Higgs boson were lighter and more discoverable, other things would change, life would be impossible and so forth, but that's false. Back in the 1970s, we had an absolutely reasonable expectation that the Higgs boson might have been 1/10 of the mass that we actually found it at, and life would not have changed in any way. There's no anthropic constraint given by the mass of the Higgs boson. You might say, well, 1/10 is not that small, but that would be another example of theists underestimating God's power. If God really wants to make the Higgs boson discoverable, he could have made it discoverable by a lot more. And that's just one example of many, many examples. Most of the matter in the universe is dark matter. Why do we call it dark matter? Because we haven't discovered it yet. Could we have discovered it yet if the parameters of the laws of physics were a little bit different? Yes, very, very easily. We have not discovered any particles other than the Higgs boson at the LHC, even though we are pretty convinced that they're there. They're just not as discoverable as we had hoped. And this goes on over and over and over again. In cosmology, you don't even need the entire galaxy to have life. Really, we could imagine a universe which was just the solar system, just the sun and the planets that we know about. The other stars and galaxies in the sky are pretty and they provide full employment for astronomers, but they are not necessary for life on Earth. A universe which was just the solar system would be really, really discoverable. We could visit it. We could go and land on the entire universe. That would be very discoverable, and it does not require new laws of physics. It's exactly the same laws of physics, just with different initial conditions. I would claim that if you really took seriously the idea that God would try to make the universe discoverable, the actual evidence of the universe provides an extremely convincing argument against the existence of God. But I also want to point out, finally, that Robin's talk is really a quintessential example of something I mentioned yesterday, which is the tendency of people who emphasize fine-tuning to be hopelessly parochial and anthropocentric. Robin talks about the fact that if the fine structure constant were a little bit different, wood would burn at a different rate and so forth. So the question is, if the fine structure constant were different, wouldn't primitive people have found something else to do other than burn wood? And that's a very difficult question to answer. You have to imagine that a physicist, given the laws of nature but not the particular values of the parameters, would be able to go, I'm sure just by looking at these formulas, knowing nothing about the history of the Earth, that the fine structure constant must have this particular value, otherwise primitive societies would not have been able to smelt metals. That is completely implausible that that would actually happen without knowing anything about the actual history. The same thing is true for other values of the fine structure constant. There's no reason to think that the universe would not be just as discoverable with a slightly different value. Thank you.
Thank you, Robin, for that paper. I think that there is probably no other person who has devoted greater study to the problem of fine-tuning than Robin Collins, and I am looking forward to his 2-volume work on the subject, The Well-Tempered Universe, which, when it appears, I believe, will be the definitive work to date on the fine-tuning argument. I don't want to take away from your 5 minutes, Robin, by having you respond to me rather than Sean Carroll. So let me just make a couple of remarks, and if you have time, you can comment. I'm struck by the fact that the alternative to theism in contemporary cosmology is this world ensemble or multiverse hypothesis. Otherwise, hard-headed scientists would not be resorting to so extraordinary a metaphysical hypothesis as that there are other unseen, causally unconnected parallel universes which are randomly ordered in their constants and quantities and sufficiently numerous so as to guarantee that finely tuned universes would appear somewhere in the ensemble. There is no independent evidence apart from the fine-tuning for the existence of such a world ensemble. The claim that you can marry inflationary theory to the string landscape to predict a multiverse, I think, is fatuous. There's no evidence for the truth of string theory to begin with, and my understanding, at least, is that inflationary cosmology is incompatible with string theory, so that the two do not yield the prediction of an actual multiverse. So it seems to me that this is quite extraordinary, and one wouldn't expect such a metaphysical hypothesis to be testable. One would basically think, well, this is a standoff between theism and multiverse or world ensemble hypothesis. And for that reason, it's all the more remarkable that there does seem to be this very powerful argument against the world ensemble or multiverse explanation that's been pressed by Roger Penrose and others, namely that if we were just a random member of such a world ensemble, then we ought not to be observing embodied, conscious agents surrounded by a universe that is in low entropy. We ought to be instead Boltzmann brains. And Robin has explained this in some detail for a number of reasons as to why that type of universe will dominate the world ensemble of universes. It would only be by adopting a special ad hoc measure of probability that the multiverse proponent could justify thinking that Boltzmann brains are less probable than ordinary observers. Now, with respect to the question of God's creating the universe to be discoverable, Robin has augmented the fine-tuning argument by showing that not only must the values of the constants and quantities fall into this incomprehensibly narrow range in order for the universe to permit embodied conscious agents, but it must also fall into another extremely narrow range in order for the universe to be discoverable by these agents. Now, it is not a refutation of this to say that we can think of other worlds that would also be discoverable or that would be more optimally discoverable. As Robin points out, that is to conflate discoverability with optimality, and that's no part of his argument. That's like arguing that a Timex watch need not be designed because it's not a Rolex. We can imagine a better timekeeping instrument, more accurate, and so forth. Therefore, the Timex is not a product of design. Similarly, to say that there could be other universes that are more optimally discoverable, or there are other universes that we can imagine that would be equally discoverable, doesn't refute the fact that we are living in a universe in which it's extraordinarily improbable, beyond comprehension, that we should exist and that the universe would be amenable to the project of modern science. And so therefore, I think Robin is really onto something here, and I hope that scientists, in keeping with their commitment to having an open mind, will entertain this hypothesis and test it and compare it with what I regard as an extraordinarily implausible alternative, namely the world ensemble hypothesis.
Thank you both for responding to my paper. Carroll has presented a set of counterexamples to my claims about discoverability, but none of my actual calculations. And I think he also, as Bill Craig pointed out, he misinterprets what I am claiming. I do not claim that this is the most discoverable of all possible universes, or that God would create the most discoverable universe, because there's other things to be considered. Now I want to look at some of Professor Carroll's counterexamples. First, he said, well, God could have created a classical world. Well, let's think about a classical world. Could you have atoms in a classical world? Well, it's well known that as the electrons are orbiting the nucleus, in a classical world, they emit electromagnetic radiation. Within microseconds or less, they will crash into the nucleus. A classical world is not stable. You cannot have building blocks of atoms out of a classical world. So that's not a counterexample at all. You need the quantum mechanics, unless you're trying to imagine a completely different kind of world that we have no sense of what it would be or its underlying laws. Now, he mentions the Higgs boson. And he's brought up to me other things, parts of the Standard Model. Well, I mean, I'll be honest, I haven't thought about much about the Standard Model. Why? Well, I've taken to heart what Carroll says about the Standard Model in his article, Why Most Cosmologists Are Atheists. Carroll claims that, quote, at least at our current level of expertise, we don't really know what the universe would look like if the parameters of the Standard Model were different. Given this, I have focused on fundamental parameters one level up from the Standard Models, those in which we have a better grasp of what would happen if they were different. Yet, as in response to me, Carroll seems to have changed his mind, claiming we do know what would happen if we changed those parameters, such as the Higgs boson, the mass of the Higgs boson, which is dependent on other parameters in at least its likely mass, in the Standard Model. And he says, well, you know, it would be more discoverable and no bad consequences would follow. That seems not consistent with, those claims of certainty don't seem consistent with what he said previously. What about the solar system example? Well, it's a single solar system within a Big Bang universe, or it isn't. If it is in a Big Bang universe, then, because you can't see other galaxies, you wouldn't be able to ever determine the universe was expanding. There was even a larger universe. And you couldn't determine the Hubble constant, and so you wouldn't be able to discover the Big Bang theory, even though it would have been a Big Bang origin. So, now, what if it's not a Big Bang universe? Well, then we're talking about a very different universe. I would ask Professor Carroll to specify that universe. What are the laws you're imagining of that universe? What's going on in that universe? In that case, then are they as elegant as the laws in our universe? Are they as discoverable? One shouldn't just throw out such a case. Then he mentions dark matter, and he says, well, we don't, just like in the Standard Model, we don't really know a lot about dark matter, what would happen if you changed its interaction. So I would just say that falls into the same kind of problem the Standard Model falls into. And then he mentions about wood burning as his final thing he says. Well, let's try to just imagine that. Let's suppose wood fires dim light, and we had carbon-based beings like ourselves. So we did it in our world. Alpha, fine structure constant were larger, no wood fires. Well, let's suppose, what are they going to burn? Well, maybe they'd burn peat. Well, the same problem with peat. Peat is made of cellulose. It's basically the same problem. Its combustion, it would emit too much radiant energy and also wouldn't burn. What else are you going to use? Well, maybe you try to use oil. But there's not very much oil around, so maybe there's a far-off possibility that they would be able to forge metals, but the likelihood would drastically decrease. They're not going to be able to use, let's say, uranium to produce heat by natural radioactivity. None of that's going to be possible. So I think that's completely fanciful to say that we'd be able to have fires just as well in such an alternative world. I see my time's up.